Today, inshallah, we'll try to finish chapter 4 on overcurrent protection. I'll try to give you some examples. I just introduce why do you need overcurrent protection? Okay, types of coordination between two overcurrent protective relays, either using current grading or time grading or current and time grading. Okay, so this is what I have reached. Okay, I already explained about these three types of grading. Now, what's the time that you need to keep between, let's say, relay number 1 and relay number 2, or protective device number 1 with the protective device number 2? What's the time difference so that these are coordinated or well properly coordinated? Okay, so that 2 waits for 1 until it really clears the faults. So the times depends on what type of technology used here, how fast it's detecting this force, and how long does this breaker takes to open this breaker. And this has to wait all of this time before really takes action to clear this fault as a backup protection. Now, to consider this, then the backup protection has to at least, take into consideration the circuit breaker fault clearing time of the remote breaker. This depends on the types of circuit breakers. Some circuit breaker can take 3 cycles to clear the fault as a mechanical device. Some takes up to 8 cycles. So this is one thing you have to consider when you coordinate between 2 different protective devices. The relay operating time. So this one will take at least, let's say, 0.1, depends on also protection time. So it will take, let's say, consider it's detecting the fault within, let's say, 0.1 if it is as a primary protection, 0.1 seconds. And then you add also a safety factor, for errors that can encounters. Error due to time measurements in the relay, errors in CTs and VT that can overshoots. Okay, if you have electromechanical relay, it will continue to move even if you clear the faults. So we call this over travel time of induction disk relays. So to do this, so generally, I should keep, let's say, 0.3 seconds as a time margin between 2 relays. And older relays, they can go up to 0.5 seconds as a coordination time interval between 2 relays. What do I need to do overcurrent relay settings? I need to know these informations. I need to know the power flow in the lines, or the current carrying capacity of cables, or the maximum power of the protected circuit, maximum rated power of the protected circuits. Based on which my pickup setting has to be greater than this nominal operating conditions. The second thing, I need to know the fault analysis. From fault analysis or studies, I need to know the maximum fault current, okay, at each bus. And normally we do, let's say, bolted, let's say there is no fault resistance. Bolted 3-phase. And also we can make other types of faults to find the minimum fault currents. Like we can also check like line-to-line fault or line-to-line to ground faults. Okay, and when the generation is at maximum generation, at minimum generation, see where is the minimum fault current, what is the minimum fault current. And also we need to know the coordination time interval, which we would get from as I mentioned, normally is 0.2 or 0.25 to 0.5 seconds. Now this is, for example, if I have this systems and I want to set fuses or circuit breakers, relays, and I have two sources that feed this radial system, then I need to make a fault at this bus, a fault at this bus, a fault at this bus, at different source operating conditions. When you have one source connected system, when you have two sources connected. And at each bus, I have to try line-to-line faults, three-phase fault, line-to-ground faults, okay, all types of faults. And then we'd like to see how, for example, this shows now when a fault at F1, which is this one, here is same as at this bus, okay. And when sources in service, when two sources in service, we call this as a strong system. When the source impedance, because these source acting in parallel, the source impedance, equivalent impedance of these two becomes small. Okay, and we call this strong system. And when only one in service, source impedance will be just one of them, and this will be bigger than the equivalent of the two. And we call this weak system. Okay, so we have to test, we have to find the faults at different, fault conditions. Okay, so for three-phase fault at F1 and phase-to-phase fault and phase-to-ground fault, at maximum source impedance with Z maximum means this is Z maximum is when you have only one in service, and minimum when you have both are in service. Okay. So when we have maximum fault, maximum Z means only one source, I have lower current, but when I have two sources acting in service, I have higher fault current at F1, similar at F2, similar at F3, as compared to only one source acting in the circuits. For two phase-to-phase faults or phase-to-ground faults, then based on this, I determine now at bus 1, I have, this is the highest fault current, and this is the minimum out of this is the minimum fault current. Now, if you want to detect this minimum fault current, your pickup setting shouldn't be lower than this, okay? Otherwise, you won't be able to detect this faults, okay? So if you look to the system, if I want to detect this fault at F3, and you have a relay here, you should know what's the minimum fault current here so that this can pick up and see it. And similarly, if this acts as a backup to this and a fault is here, this should be able to detect this fault when this fault is minimum. So when you look to this, I should know this should be graded with this one, okay, at minimum fault current also. It's not just as maximum fault current. Now, how do you coordinate between these different types of protective devices? Now, suppose I have a fuse, which is here, and I have a circuit, a relay on top, okay, before it. So I want to coordinate a relay with a fuse. A fuse characteristic something like this, where we have two curves that represent the operating time of a fuse. So this represents y-axis the operating time versus the current, and the lower curve, which is this one, represent the melting time of a fuse. Normally, a fuse has an element, so fuse. Okay, it has end cups. Okay, and inside, and this has a container. Okay, Inside there is small wire, or sometimes we call it, this is element, fuse element. This fuse element is once a current flow on it, it will heat up, and it melts. Once it melts, break, and once it breaks, it's open the circuit that connect this side to that side. So this is just in cups where it's made of, let's say, conducting material that links the fuse element from the two sides. And so there is one curve that represents the melting of this fuse element. So this curve here represents, let's say, at this current, it takes this time for this material to melt. However, melting of this material doesn't mean the fuse has broken, okay? You need more time until once this fuse element has melted, a gap is created, okay? But a current still flow due to arcing between these opened points until you clear all this arc between the open point of the fuse element. Then we can say then the fault is cleared. So the times taken for this spark or arc to extinguish, it takes this time from here to here at this condition. This is the arcing time. Okay, so at that time, or this is the time now taken for clearing faults. So we call this total clearing time, okay, characteristic at which the fault is totally clear. Now the fault is the 2 points are really open. There's no current passing anymore. There is no arc. This is the fuse characteristics. And normally we have to look at these two curves when we coordinate with other protective devices. Now, this is the characteristic of a relay, and normally we take extremely inverse. Okay, well, I want to coordinate with fuses, we use extremely inverse. I would say extremely inverse. I already mentioned about standard inverse, very inverse, extremely inverse. Extreme inverse almost becomes parallel or very close to the fuse characteristics. Okay. So it matched instead of something like this. All right, so how do we coordinate between fuses and this? We go to at maximum current at fuse blows, which is this, okay? And we add 0.15 seconds, okay, between, and we choose the time setting that gives me this time at this fault current, and I will choose the curve, the time dial settings of this relay, of the 51. We are talking now, this is the 51. The 50 is the instantaneous. Okay, so this is a few after. There are other types of fuse which have explosion type. They call it fuses, where their characteristic is like this. This is the melting time. This is the total clearing time. And similarly, at maximum fault current at which the fuse blows, okay, I have to add 0.2 seconds here. And then I choose the curve that gives me a coordination time of 0.2 seconds. So for all the cases, the relay should be above, okay, the total clearing time. Should be a clearance between. And now when I coordinate between a relay and low voltage breakers, like molded case circuit breaker. In this case, this is the circuit breaker that we have at home, for example, fixed near to in the meter box outside. So this is how do you coordinate this? This is the characteristics of molded case circuit breakers. And similar, it has two elements inside. It has bimetal elements, which is represented by this part. And this is provided for overload protection, and has magnetic elements, which is indicated by this characteristics, which is very fast, like instantaneous. So we have something equivalent to 50 and 51, but mechanical devices inside circuit breakers. So to coordinate, we have to go to the instantaneous part here. What is the maximum fault level at which I want to coordinate between this? So in this case, I will see what's the fault closest to this breaker. Okay, and what's the maximum fault at this level at which this would operate? So this is the maximum fault level. And at that point, I have to leave 0.2 seconds and choose the settings, time setting of this that gives me, okay, this characteristics. And I can go if we have a relay with a relay, okay, this coordination time should be, depends on this. Is this electromechanical with electromechanical? I have to keep 0.4 seconds at also maximum fault. Where's the maximum fault? When a fault is very close here at this relay, and I should see what's the operating time of this, which is this value. This is maximum fault, and we add a coordination time interval to get this point, and from which we find the time dial settings of the upstream relay. So that's generally for relay to relay. If this is a numerical relay and this is numerical relay, and this fast breaker, this time can go to, let's say, 0.2 to 0.25 seconds. Okay, depends on now the circuit breaker operating time, this technology used. So that time difference between two relays, coordination time, this is what we call this coordination time interval. All we are talking about coordination time interval between different devices. So in this course, mostly I will cover coordination between relays. Okay. How do we, what are the procedure now that we need to follow to set a relay, current and time settings? I need to select the appropriate relay characteristic. Is it standard inverse, very inverse, extremely inverse? I choose the CT ratio. I have to select the current settings for the phase over current relay. We say we have three-phase systems, and I have three CTs here to, right? Each CT have, it will go to one phase over current relay, or to, and this then will be to ground, and this goes to the common ground, which is this with this with this. Okay, so when we look to this as 51 relay, here we can have 50 and 51. Now have to have time setting, okay, and time dial setting. The pickup setting, I pickup setting, and time dial setting, I'll say I pickup setting, BU, or sometimes I make it as I setting. So this relay needs, for these three relays, we call it the phase of our current relays, and this is the ground over current relay. Okay, so these are the phase over current relays. Now, what are the current setting I and time settings of this, and what is the also current setting I and time settings of this also. So these we need to know. Select time dial settings, as I said, for this is also called, instead of time dial settings, also called time multiplier setting. Instead of time dial, we call also them TMS. Make sure that downstreams, suppose this feeds, this is a feeder that feeds a load, and they have another protection. This has also to coordinate with other relays downstream. These are the standard characteristics according to IEEE standards. We have CO11, which is extremely inverse. This is where we use it to coordinate with fuses. We have very inverse and inverse and moderately inverse, and definite minimum. Definite minimums, like there is no, it's not inversely proportional. It's almost same time regardless of the current. Okay. We have also the IEC standards. They have defined also these characteristic as normal inverse, okay, very inverse, extremely inverse, long time inverse, and these are the IEEE standard definition for time current characteristic of overcurrent relays. Some manufacturers, they have their own characteristics, okay. So in relays, in numerical relay, we need to model these, okay, equations for these equations to implement them in numerical relays. In electromechanical relay, all of these, each of these curve has to be implemented using one relay, okay. While in numerical relays, these are an equation I can choose from a library of curves, which one you want to use, okay. So for the select the characteristic, normally normal inverse are used, extremely inverse are used when you have you want to have to protect with extremely inverse. Now we want to have protection with the fuses, okay, or distribution transformers. And these are when you have normal inverse and very inverse, okay. You need when you have current difference between two buses, okay. Suppose the fault current here and fault current, like here, fault current and fault current, there is a margin between them. Then you can use these standard inverse characteristics. So now, how do you select then the CT ratio? You select CT ratios based on two criteria I mentioned before. Criteria one, that the rated primary current has to be greater than the rated primary current of the CT. Suppose I have a CT, I want to find what is X to 5, and X is the primary rated current, and this is the rated secondary current of the CT. I want to know the ratio required for the CT. So you have two requirements. First, the primary rated current, which is this X, has to be greater than maximum load current. So I load, I full load, I nominal. Okay, I full load. Second, so first condition, that X has to be greater than I nominal current of the protected circuit. Second, that we want also, the second one, we want also to reduce the secondary current, this secondary current, to 20 times the rated secondary. So I want the second condition that when I take I fault, now there is a fault here, maximum, you divide it by this CT ratio, you should get 100 or 5 times 20. 20 is the standard by IEEE standard. 20 times the 5 is the now we want to reduce it to 20 times 5, so from which also you can choose the ratio. So I want to, when I take I fault divided by the CT ratio, so it means times 5 over X, okay, should be this value. I want to make it less than or equal of 5 times I nominal, sorry, 20 times, so 20 times I nominal. Twenty times I 20 times 5. The 5 here, this is to 5. This is to 1. This is 1, 1. Now 5 with 5 goes, so X has to be, as a condition 2, has to be greater than or equal I fault over 20. So this condition X has to be greater than your full load, but X also, if you want to make this ratio so that the secondary current reduced lower than 20 times 5, the ratio primary rated current has to be greater than I fault over 20. So these are the two conditions I need to consider when I choose a CTs. Condition number 1 is must consider, and this condition 2 is optional. Okay, so you have to satisfy 1. This 2 is not necessary. This is the must you have to satisfy. How do you choose the current setting? In electromechanical relays like this one, we have a plug. This is the plug. Okay, it's a sort of, you can put it here or here or here. Okay, so as you change it from one hole to another, you are changing the pickup setting. So suppose here at, let's say, 0.5 ampere pickup setting here, 0.7 ampere here, okay, and so forth. And this is called the plug setting because it looks like a plug in electromechanical, or we call it tab setting because this is one tab, a second tab. Okay. However, in numerical relays, we don't have this plug, so we can call it just a current setting. Okay. So this is the current settings in general. So we choose this. How do you choose that current settings? Based on the following criteria. So the first one, that the current setting has to be greater than your full load. If I choose a current setting lower than my full load, then it will operate during normal operating conditions, while the protective device should only act so when you have a faulty conditions or abnormal condition. So your pickup has to be greater than your maximum load, okay, or your full load, I nominal, okay, maximum. So even you should consider a short-term emergency. If you have a motor that can also handle 5% overload, I don't want to choose my settings at 5% over the full load. I have to allow a margin higher than this. So when I go to 1.5 higher than this, I have this 50%. I am away from the full load current. So anything higher than 1.5 generally, this means abnormal conditions, and thus I can declare this as a fault. And similarly, the setting has to be not greater than a maximum fault current, minimum fault current. If it is greater than minimum fault current, means this relay will not discover this fault. So if you're sitting somewhere here, when a fault occurs, this relay will not see this. Not see it means it won't pick up. Okay. So your setting has to be always, okay, somewhere between maximum load current to a minimum fault current. That's why from fault analysis, we need to know this, okay? And also we need to know this because we coordinate time based on maximum fault current. So settings, generally, it can be 1.5 to 2 times your full load to 1/3 of this. I want to be away from minimum fault current. So I want to, this is the pickup setting. Normally pickup setting, the relay is connected at the secondary of a CT. So this is the CT and it's connected to a relay where I want to know what's my pickup setting IS and time dial setting TD or TMS, time multiplier setting. So now to choose this one, I pickup setting, because the relay at the secondary side, and this is I nominal of rated current of this circuit, and the ratio, this is the CT ratio. If I have to take something, the pickup setting has to be greater than this, but the setting at the secondary side of the CT, I have to take this one and divide by CT ratio and take something greater than, so I nominal divided by CT ratio, I'll get this one. And I have to take a setting greater than this by choosing a factor greater than 1. So this factor is the overload factor, we call it. So overload factor for protecting electric motors, I can choose 1.15 if the service factor is something called service factor. If the service factor 1, I can choose the pickup setting 1.15. If the service factor is 15, 1.15. Okay, I can go to 1.25. So generally, I shouldn't go below than 1.25. Okay, if you don't know the service factor. So service factor are, the manufacturers design the motors that can handle 15% as overload, okay, over its rated current. So you want to trip the motor when it is, let's say, at 10% higher than its full load current. And for, let's say, lines or transformers, we can go to from 1.25 to 1.5 as an overload factor. So I'm going to go to 50% higher than full load. Anything higher than 25%, 50% of your full load, that's declares a false. For transformers, or we can go even to 2 times. For the ground over current relay, which is the title for this one, I don't consider the full load current, okay, of the circuit, because there will be no current even at full load current in the 3 phases. There is no current in the ground here. So this pickup setting shouldn't be taken considered higher than this. So at normal conditions, this normally is 0. Anything higher than 0 is sufficient to declare that there is a ground fault. So this is IG, okay, I ground current. So this is normally equal to 0. So picking a setting higher than 0. So let's take, we take 10% or 20% of this sufficient as a settings for the ground over current relays. Something higher than normal current that goes in the neutral, okay, or the ground during normal operating conditions. So I can take 20% of the full load nominal current divided by CT ratio. And sometimes we can go to 30% on instead of 20%. Now timing, time setting of this relay has to be considered based on the coordination. This is the top here, which represents the time dial. We can move you move this contacts. This is the moving contact, and this is the fixed contact. If you move this is closer to this, you will take less time to operate. If you move this farther away from this contacts, you will take longer time. And by moving this farther away, okay, or closer, you control the timing, operating time. And this dial is called time multiplier setting or time dial setting. So this is the dial, because you dial this can be moved this side or that side to control this one. Okay. So how do you choose this time setting? We choose it based on the following criteria. Okay. That suppose I have two relays. This is not the latest slide that I have. Suppose I have this bus A, bus B, bus C, and I have two relays I want to coordinate. Relay A and relay at B. Okay, now I want to choose the time for this. Okay. So how do you choose time of RA? I have to choose the time setting such that it gives me enough time between this. So time at A should be time of the primary. So this is now, I'm assuming this is primary, this is as a backup now. This is the load side, this is the source side, and this is the load side. Okay. So this is time at relay B plus the coordination time interval. So I have to choose a setting, time dial setting of this that provides to me the time required for this to operate plus a coordination time interval when this encounters a fault is here. You coordinate normally between these timing when a fault here closer to RB, you calculate the time of this at fault very close to RB, okay, and you add a coordination time interval to it to find the time of this. Based on the time of this, you select the time dial, okay. I'll keep you to read this ones. I'll go to directly this example. I'll give you two examples that covers all of what I wanted today. Suppose I have a radial system. I have three sections on this radial system. I have load is mentioned here, okay, the maximum load, and I have also the maximum fault current. Fault current is here is 2000 ampere. Here is at this bus 2500 and so forth. The fault at this bus is 3200. And for these are overcurrent relays, and the CT ratio are given to you, okay. And I want to check now the I want to allow 30% as overload margin. So expect that this is an overcurrent of higher than 30% of the full load. These are the full load now. These are full load or the maximum load now. I want to allow 30% over this full load before the relay declare that this is a fault. Okay, so you have a 30% allowable allowance for overload, and coordination time interval is 0.3 seconds. So time between this should be not less than 0.3 seconds. And you have a plug setting, the pickup settings from 50% to 200% in steps 25%. So the relay, the pickup settings here, this one, So I started from 20%. It's a 25, sorry, percent. Okay, then 25 each, then 50% up to last 200%. This is the available setting. So 200% of what? Of the 5 ampere. So that's correspond to 10 ampere. And that's correspond to 25% of 5. Okay. 50% of 5 is 2.5 ampere. Okay. And that's quarter of the 1.25. Okay. Ampere. So these are the available settings. So which one of these would select, and which dial setting you need to select for each of the. Okay. Sorry, it's starting from 50 rather than 25. This is from. I don't have 20. The minimum is 50. Okay. I don't have this setting. So how do I, the voltage here at this bus is 11 kV. So this is 11 kV. Okay, so this is a three-phase system. And also I want to determine the operating time for fault at bus 4 and bus 1. When a fault at bus 4, what will be the, once I finish from step 1 setting these relays, I want to find the operating time when a fault here and when a fault at 1 here. Okay. Let's get started now. What I wanted to find, what is the I pickup here? I setting, pickup setting. And what is the time dial here? Okay, or TMS. And similarly, this is for phase over current relay, or considering the phase over current relay, not the ground relay. Okay, and this is only for the 51 relay, not the instantaneous. And similarly, I want to find current and time settings for this and this. So where do you start? I'll start with the finding I nominal current that this will see. What's the nominal current? I'll call this I nominal 2, I nominal 3, and this is the current, full load current this will see. I'll call this I nominal 1. And what is the full load current this will see is this load, right? So from this load, I'll be able to know the full load current that this relay will see. And similarly for this, I have to add these two loads to find the full load current that this will see. And for this one, I have to add the 3 loads to find the full load current that will see. And that then we can calculate the pickup setting. So this is what I'll do. And nominal currents, I took the for number 1, I nominal 1. For this one, I added this plus this plus this. Okay, which is 5 plus 3, 8 plus 8, 16.5 MVA divided by root 3, 11 kV. I got the current, nominal current here, I nominal 1. Okay, I also get this is I nominal 2. And this is I nominal 3. So I nominal 2, I take also, this and this. I got this current. For nominal 3, I have just 5 MVA. I got this 3. And then I can choose now the pickup setting. Pickup setting is the sometimes we call this pickup PU. Okay. the pickup settings or I setting is equal to overload factor times nominal full current divided by CT ratio of relay 1. Now I choose overload because I have to keep a margin of 30%. I will go more than 30% as a margin, more than 1.3. Okay, is 1.5 times the full load current divided by the CT ratio. I get this. This is the setting of relay number 1, and similarly for relay 2 and relay 3. Okay. So for relay 1, the pickup setting has to be greater or equal to this or very close. So from the available settings, from 50%, it represents 50% of 5, which is 2.5 ampere. Okay, I have 75%, which is in steps of 25, then 100%, which is 5. So I need 7 pointer. Which of these is 7? It's 150%, right? So at 100 and 125, then 150, then 175%, then 200%. These are the available plug setting. Okay, so from here, this will be like 150% of 5, which is 7.5 ampere. So this has to be the pickup setting closer or higher than this. So I'll choose 150%, which is correspond to 0.5 pickup setting. And for this one, 6.3, I chose also because at one, I'm not sure this is right. At 5, what's 125% of 5? Okay. In this case, I have this is 6.25. Ampere. So this is higher than, so I choose the next setting, which is 7.5. And similarly, this one, this is 4.9, which is closer to 5, which is 100%. Okay. I'm finished from the first step. How do you choose the pickup setting or the plug setting? Second is the timing. Timing, I should always start from the last and choose the minimum settings for this so that this clears the fault at minimum time. Then I go for this one by coordinating these two relays together. Then I'll go for this by coordinating these two together. Timing, I'll choose a setting first. I'll start for the relay 3. I'll choose my minimum operating time dial, which is 0.1. This is not second, it's 0.1 as a time dial. And then I'll check the operating at this minimum. I need to check the operating time of relay 3 when I choose this settings so that I can coordinate with the downstream protective. Suppose I have this load has also protective devices somewhere here. I want to allow some time for these to take action. Okay, I don't want to clear this, so I want to allow at least 0.1 seconds, timing to coordinate between this and the downstreams if there are downstreams protective devices. So I started now. It's just to check. This is the to check the timing. So what I did, I created a fault here, very close here, which is at this bus, which is 2000. I will see what's the operating time of this. If this more than 0.1 seconds is fine. I will keep the time setting as it is. So I created a fault. So at fault 2000 ampere, which is the remote fault bus current. Now I see the plug setting multiplier. The plug setting multiplier is the ratio of the fault current to the pickup setting. So the fault current I have to divide by CT ratio to transfer to the secondary side, okay, because the setting is already in the secondary side of the CT. So 2000 times 500 over 400, which is the ratio of this one, it gives me this current. What I did, I transferred 2000 to the secondary side of the relay, and I'll divide this by its pickup setting. I'll see this fault current how many times higher than this. Okay, it is 5 times. And then I use the he told me use these which characteristic I'm assuming here standard inverse characteristics. Yeah, here standard inverse characteristic is used, and the standard inverse characteristic is we have it from the standard. I don't know if I have it here. Oops. Yeah, so these are the equations that represent the standard inverse characteristics. This is the moderately inverse, extremely inverse, okay, very inverse. These are the according to IEEE standards, okay, characteristics. But I want according to the one I choose, and the problem is the standard inverse characteristics. And this is the equation that represent the operating time versus the pickup. This is the IR represent the ratio of the fault to the pickup setting, the one I calculate, or we call this plug setting multiplier. And this is the time setting or time dial setting. The difference between IEC standards, okay, it is used TMS, and here they use TD, time dial. Okay. And IR here represent I fault divided by setting, current setting. I fault divided by CT ratio, okay. So I fault refer to the secondary side divided by the pickup setting. That's, we call it the multiple of the pickup settings or plug setting multiplier. Sorry, yes.
دكتور هاي السلايد من وين دكتور؟ مو موجود، انا طابع النوتات بس مش موجود عندي هاي الشيء.
هذه من احد الريفرنسز. اوكي، انا عندكم already هالكاركترستيك في one I kept it in one of the, I think it's on chapter I'm talking about 5 direction relay. No,
يعني نحصلهم دكتور في البلاك بورد.
This is overcurrent relay standard inverse. These are okay.
اوكي دكتور.
So I know the equation that I want. So we have, either I give you the equations or I give you the curves. Okay, where's the curves? These are the curves. Okay, or the standard inverse, definite time, very inverse, extreme inverse, or like this. Okay, I'll give you this curves that represent the relay. This is DMS. Okay, this is the multiple of current settings, which is the ratio of the fault referred to secondary side with the CT to the current settings. All right, so now I'm using the equation rather than the curve. Okay? In the next example, I'll show you how to use the curves instead. Okay, so from that equation, which is TMS 0.14 over IR in the what I showed you here, it's the plug setting multiplier. Okay, multiple of represent 5 times the pickup settings of 5. This is the pickup 5. Okay, so 5 over 0.02. So substitute and time dial, I choose 0.1. I get 0.4 second, which is sufficient enough to coordinate with any protective device downstreams. If this is much less than 0.1, then I need to think of increasing this. So I will start from minimum time dial for last one starting point. I'll just check the time. Now then I'll decide it, oh, 0.1 is okay, sufficient. Okay. Then next I will go with R2, relay 2. I need to coordinate between this and this. I already chose the setting here to be 0.1. Okay. Then what I have to do, how do I coordinate this with this? I have to create a fault. Okay, I have to coordinate this and this at maximum fault that this C at R3C. So maximum fault that this C is the fault to 2500. When a fault very close to here, when almost at this bus, when a fault is here. So I have to coordinate between this and this at this fault current. Okay. So I have to also use the same thing. Okay. This is the time. I have to calculate the time for R3 at this fault current. And then I will add coordination time to know the time of this, from which I find the time dial. So timing of R3 at fault 2500 is substituting here. Timing of R3 is known, which is 0.1 from the previous step. And the current is 2000. I have to refer it to the secondary side to 2000 and divided by the pickup setting. This is this ratio. Okay. Minus 1 give me 0.3 seconds. So this would take 0.375 seconds to operate. I have to add coordination time interval, which was given in the problem as 0.3 second, the grading margin or time grading or coordination time interval. So relay 2 has to operate not less than 0.2 second in order to properly coordinate with R2, with R3, sorry. Now I know the time that this should work. Now I need to select the time dial by substituting the sum. So time is known of R2, TMS is unknown of R2, and I know this one, okay, because I know the fault level. I know it's all system. So I'll just find TMS equal to this times this, okay, over that one. So time 3, which is time of, not 3, sorry, this should be of 2. This is of 2. Okay, I'm trying to find the settings of this 2. So time dial, time multiplier setting of 2, time of relay 2, time block setting of 2 over this. So from that I'll get the time dial, okay, at 0.12. Then similarly for R1, sorry, to coordinate between this and this, I have also to apply, I have to coordinate between them at maximum fault current that we'll see, which is this one. I don't take this consider. So you consider now coordinating R1 and R2 at maximum fault current that this will see, which is 2800. Okay. So that's what the current. I calculated TR2 first, and I know the settings from the previous step. This current referred to how many multiples of the pickup setting of R2, and I get the time. I added coordination time interval. To this time, I get the time that suppose for which R1 has to operate, and from which I can find the time settings of TMS1. I repeat the same steps as here. Now we can determine the operating times at Now from here up to this step, we finish the settings. Okay. From this settings, if I plot the curve, the three curves, right? The relay 1 is the pickup setting is this, and this is time dial setting. Relay 2 is this pickup and time. These are the three settings. When I draw the three equations, this now, what I did, I am changing I fault, which is here. I pickup is known, CT ratio is known, time dial known. I plot this as a function of I faults for the three relays. So it gives me these three curves. From 2000, I plotted to 3200 ampere. And as you can see, this is relay number 1, relay number 2, and this is relay number 3. And relay number 3 works first, right? Because slower. So at any current, this takes this time. If relay 3 fails, because this is the system, relay 3 should work first, then 2, then 1. So in this case, they are well coordinated, and the difference between this has to be not less than the coordination time interval. Okay. Now, if you look back to the system, I coordinated between this and this at this fault current. So at this fault current, 2000, which is somewhere, 2000 is here, no, 2500, which is here. The operating time was 0.375, I got here. If you add this coordination time interval to it, I will get this one. We choose this point from which we found that curve. Now, when we coordinated this with this, we coordinate at 2800. This one. When I found the operating time of R2, okay, and added a coordination time interval, okay, and found this point, 0.9 seconds, and from which I found this curve. Okay. Now, if the current now, if you go higher, you'll see this is lower than 0.3 seconds that we want as a grading margin. We need a grading margin of 0.3 seconds. If you look for fault higher than 2500, relay 3 will not see faults higher than 2. Fault higher than 2000 means somewhere here. So this will not see any current higher than 2000. This will not see currents higher than 2000. This will not see currents higher than 3200. So plotting a curve of R3 beyond 2500 is useless. So after 2000, I can stop the curve of R3. So R3 up to 2500, up to here. So this is like, I don't have to draw it because relay 3 will not see any current higher than 2500. Okay. And similarly for relay 2, higher than 2800, I will have useless to draw this point because it won't see force higher than this. I can plot this as a dotted line if I want. It's useless. And now for relay 1, it will not see currents higher than 3200, so I can stop up to 3200, but anything higher cannot draw. Now, how do we reduce the timing? I have one more example I want to show you. For those who want to leave, they can leave, but I want to finish this and it will be recorded, okay? For those who will leave and join later to watch the second example. Now, in order to reduce the time, the timing of, suppose now, a fault occurs, because a fault occurs very close here. this guy still needs to coordinate with this because it's already adjusted so that it should wait for R2, R2 wait for R3. And because of this, this will wait a long time, okay? So of course, for it's very close to the relay 3, relay 1, sorry. Suppose fourth is very close here. Although this will not see the fault, this is also will not see the fault, this will take this time to operate. So it's a very long time. Okay, and our objective now, how do we reduce this time? We can reduce it by, okay, I can reduce it if I choose another color. If I can add now, relay 2, relay, sorry, 3, why it should wait for this down? If the fault is higher than 2300, it means the fault is somewhere here. If the fault is here is 2000 ampere. If the fault here will be higher than 2000 ampere. If the fault here, as it goes closer to the bus tree, the fault will becomes higher than 2000 until it reaches 2000. And similarly, this relay, when a fault higher than 2000 means the fault is here. So why should this wait for the R3 when the fault is 100% guaranteed in this in line 2, 3? And similarly, why R3 should wait for downstreams relays or protective devices when the fault is 100% guaranteed in this line? So here comes the advantage of adding instantaneous relay that acts instantaneously if the fault 100% guaranteed in this line. Okay, so how do I guarantee the fault is here? When I see when this sees a fault greater than this, then I don't want to greater by a margin, let's say 25% higher than this, then the fault is in here. I don't have to wait for a time delay. This can act instantaneously. Similarly, this can act instantaneously if the fault, if this measures a fault more than 2000 by 25% higher. Okay, so that this acts instantly in a state of waiting. Similarly, here. So by adding instantaneous relays, so when this sees a fault higher than this by a margin, I want to act instantaneously like this. Okay, sorry, it's not. So when R3 sees a fault more than 2000 by a margin, let's say 2200, 2000 here, 2200 or 1500, for example, here. I don't want to wait till downstreams. I can, so the curve will becomes like this. And this is when I add an instantaneous relay, okay, with R3. So this is the 50 relay at R3. Similarly, here I don't have to, R2 shouldn't wait for R3 if the fault higher than 2500. Suppose at 2600, which is this one, this relay shouldn't wait for the other relay. So 2600 somewhere here. So I want to add an instantaneous relay here. Okay. So this represents the 50, 51, and this represents now added 50 over current instantaneous relay for R2. This is 50 of R2, 51, sorry. Now, any faults, similarly for the last one, anything higher than 2800, this should act immediately by a margin, let's say, suppose higher than, let's say, 2900 or 3000. I would want to wait for this direct. So 2900 or 3000, I want to act immediately. This is 3000. Okay, so that's an instantaneous 50 relay for R1. And this is 51 relay of R1. Now with this, if I put relay here, which closer to R3, it will not wait this, it will instantaneously trips. And now I have achieved two things. I achieved selectivity and I achieved fast operating time, right? By adding now instantaneous relay in addition to, for what's the advantage of adding 50? I will reduce the operating time, okay? And also it can be used when to avoid loss of signal. Suppose you have relay, two relays. This is the downstreams. So suppose this is two relays. This is let's say R1 and this is R2, and this is suppose R1 and this is R2. Now up to here, from here to here, these are well coordinated because R1 should, this is the load side, okay, this is the source side. So R1 should work before R2, like at this current, this work this time, then R2 operates. Up to this point where R2 operate before, so this is a miscoordination in this case after this point. To avoid this, I can add instantaneous relay with R1, so it will operate that this way. So I avoided the cross section, and now they are properly coordinated. Now, how do you set this 50 relays? How, when I say I want to make this one relay pickup setting higher than this by a margin, so what's this margin? I should keep this instantaneous relay setting higher than this by how much? Now, this is the general rule for lines between substations, between buses. I can keep 125 to 130%, 135% of I fault at the remote station. This is remote or downstream. Okay, so it means if I have two relay at the same thing, so I have one here and I have one here, okay, and I want to coordinate between this. So I want to find the instantaneous here. So you have to so if I want to choose for this, I have to for this is the remote fault, okay, and I have to choose I fault at remote for this relay to set this one. Now I choose this fault ruling where I added to it 25 to 35% more, and that's the current settings for this relay, this one. And this 25 or 35%, is given such that this, even if you have a decaying DC offsets, okay, it is taken care of. Similarly, transformers, I can take 125 to 150% if we have transformer. We have one transformer, and suppose I have at HV side. This is HV side. This is the LV side, okay, of the transformer, and I want to find instantaneous setting 51 settings. Sorry, 50 setting. This is now we are talking about the 50. The setting, the 50 setting at the HV side. How do you set it? You create a fault at the LV side. You refer this to the HV side, and you take 25% to 150% higher than that current referred to HV side, and that will be your setting. For distribution lines, suppose I have now a load, and I have an instantaneous here. This is the load. It could be a motor. And I want to find what's the instantaneous settings for this motor. So generally, I can take the fault, local fault current, I fault local, because I don't have remote, right? So I take 50% of the fault local, okay, or 6 to 10 times higher than my maximum circuit ratings. So I take either 6 to 10. Why 6 to 10? Because if we have a motor, normally the motor current, it has a starting current. This is the current versus time. So the motor current starts like this, then goes to maximum, then goes to full load. Okay, so this is my I nominal, I full load of the motor. Okay, but this is the starting current. That's I starting. Okay, I starting normally depends on the motor side. This can go to 6 to 10 times than IN. Okay, so if I choose an instantaneous relay at this value, it means whenever a motor starts, will always trips. Okay, so my setting has to be greater than the starting current. So setting has to be greater than 6 to 10 times. Okay, so I have to choose I have to know what's the starting current, and I choose something higher than this by also a margin. Maximum. So once I finish the coordination, I have to, I will just apply these criteria for the next example. I should use this version. So this is the next example. I have this system, three-phase system. I have at this bus C 3 loads, each 3 MVA, and I have one protection devices for each feeder. Okay, so I want to find the settings here. I have a line or cable that connects this bus to this bus, and the line cable resistance is given here, and At this bus, I have also 3 feeders, okay? And I have a breaker for each. Similarly, I have transformer that connects this bus to bus B, and they are giving the specifications, the voltage ratio, the MVA rating, and the per unit impedance of this. And I want to know the settings of these 4 relays, the time and current settings. So I want to calculate the nominal currents and the 3-phase short circuit levels at each breaker. And now this includes also short circuit calculation of the maximum fault at each bus. And I want also to select the transformer ratios of the CTs. I want to determine the values of the pickup settings, time dial settings, and instantaneous settings. I want to choose the percentage of line BC that will be protected by the instantaneous relays. And I want to draw the time current characteristics. And you have to take, when the design, you do this design, I need to consider the following information. Discrimination margin, which is the coordination time interval. This is the coordination time interval as 0.4 seconds. And we have inverse time characteristics shown here. This is the timing, time characteristic. In the state of equation, we'll use this curves now. And relay, the pickup settings of the relay, available pickup settings from 1 to 12 ampere in steps of 1 ampere. And the time dial settings is time dial setting from the curve, okay, from half, 1, 2, up to 11. This is the time dial. Okay, time dial settings. And this represents the multiple of the value of the multiple of tab value current, or this way also the plug setting multiplier. And this is the operating time. Okay. And instantaneous relay, we have settings available from 6 to 144 in steps of 1. So how do we start our setting? I will start our setting from knowing the full load currents and the fault levels first. Okay, so I'll start with, to find the fault levels, I need to draw, okay, the impedance diagram of this. So this is what does this represent here. The short circuit level at this bus. When a fault here, normally short circuit fault level is given either in MVA or given in ampere. So S short circuit, is given as, if I know fault is √3 V line at the bus, okay, rated, times I short circuit. That's MVA rating. This is this. Now, instead of giving in current in kiloampere, they will give it in volt ampere. Okay. So if I would like to know the current, I'll use this equation to find what will be the current when a fault at bus A. Okay. Similarly, I can find also the source impedance. Okay. To find Z source, what is the equivalent impedance behind this bus? So Z source equal to V source over I fault. Okay. When you apply a fault here, you have the fault current. I know the voltage, phase voltage, of course. Okay. This is the phase voltage at the source over the current. That's also equal to, right? If I substitute this there, I'll get Also V square, V line square over S short circuit. Either this will give me the source impedance behind this bus, or this is like the Thevenin equivalent circuit, okay, of the circuit below or behind bus A. So I can draw, this is like a Z source, and this is the Thevenin equivalent, the V Thevenin. Okay, this is Z Thevenin. So this is how do you find this source impedance that represent the circuit behind this process by using this. Now, because with this I will be able to draw all the circuit. This represented by impedance, this represented by impedance, then I can find the faults levels. So first, Z source with V line square divided by S short circuit. Okay, I'll get 115 is the voltage at this bus. The voltage at this bus 115 kV. And voltage at this bus is 13.2 kV. And this also 13.2 kV. Okay, so as I get 115 square over the short circuit level 915 VA. I get Z source impedance. This impedance refer to 115 kV. Similarly, Z transformer, which is so this transformer, this is the per unit impedance. And I have also, I can find its ohmic value, refer to the HV side or refer to the LV side. So the impedance from power system 1 is an ohm. It is the per unit value by Z base, and Z base is V line square over S base, and S base is the power of this 25 MVA, and I get the ohmic value of because I use 115, so this impedance refer to the HV side of the transformer. ZBC already given to us, the impedance of this line, okay, refer to the 15 kV side is 85.35. Okay. Now I draw everything referred to the HV side, so I can draw the equivalent circuits, okay, which is this one. The HV side, now this is the bare phase equivalent circuit because for three-phase fault, it is a symmetrical fault and we can use bare phase analysis. So the voltage at bus A, it was 1115 over √3, this is V phase. And this is the impedance of Z source. This is the impedance of the transformer. And this is the impedance of the line. All of them refer to the 115 kV side. Now I can find the fault at C. This voltage phase voltage over the sum of the three impedances. I get the fault at bus C. But this is referred to 1115 kV side, but bus C is already in the 13.2 kV side. I have to refer that current to the 13.2 kV side again. So I just use the voltage ratio, this current which is referred to this times 1115 divided this, I get the fault current at the 13.2 kV side. Similarly, a fault here is this voltage divided by sum of these two. I got the current at fault at B, and for B already also in the 13.2 kV side, so I have to refer it to 13.2 kV side. This is the current referred to 13.2 kV side. So I have got, this is the fault current for bus C, fault current bus C. For bus A already in the 115 kV side, so I don't have to refer it. So it's just this over this impedance. I got this is the fault current referred to 115 kV side. I got the fault currents. Once I get the fault currents, I can also calculate now also the full load current. The full load currents you are given here to find what is I nominal 1. This is I nominal 1. I have to take this nominal power divided by √3 times this voltage line to line. Give me this nominal. What is the nominal current here? Nominal 2. Nominal 2. I have to take the 3 currents here. Okay. So 3 times this, or the summation of this, right? Now, how to find the nominal current here? I nominal 3. I have to add this plus this plus this, but because I don't know these two, the maximum of this will be the maximum rated current of the secondary winding of this transformer. So I will get it from this rating and the low voltage side. And this is I nominal 4. I nominal 4 is obtained from also the rated power and the rated voltage at the HV side. So this is a straightforward. I nominal 1 is the power of the load, which is S load. Normally we take S over √3 V line. Okay, I got this is the this is V line. This is the current, full load current, I nominal 1, 2, 3 times this. 3, we talk the power rating of this and divide by 13. So 25 MVA, okay, divided by 13.2 kV, give me the the current at the 13.2 rated current. And this is at the HV side, same 25 MVA, and I get 25 ampere. So these are the nominal current that I need to use to choose the pickup settings of the relays, the 4 relays. And this is the short circuit values. Now, how do you choose the CTs now, ratios? Now, CT ratios, I have to use these two conditions as I explained before. I don't want to repeat. For relay at breaker 1, this is the nominal current we calculated from this step. This is a summary, okay, 131.2. And this is the short circuit current at bus C, which is 4640, okay, 4640. And now, to choose a CT ratio, we have to specify this two conditions. First, the CT ratio primary rated current has to be, the CT primary rated current has to be greater than my full load. So if I want to consider only criteria 1, I have to choose 200 to 5. Okay, but if I want to also to satisfy condition 2, as I mentioned, I have to, I showed it to you, this is I fault maximum divided by 20. Okay, if you divide I fault maximum, which is this at bus 1, divided by 20, I'll get this. Okay. Now, if I want to satisfy both, the primary rated current has to be greater also than both, than 131.2 and 232. So I'll choose it to 300, higher than the highest of these two, 300 to 5. But if based on criteria 1, which is the must satisfy, 200 to 5 is sufficient. So this is based on both criteria, okay? So based on both criteria, both 1 and 2. All right, now similarly for breaker 2, we found the full load current is this. Now if I want to choose based on criteria 1, 400 to 5 is sufficient. However, when this 400 to 5 will not reduce the current at the secondary fault current to less than 100 ampere. And if I divide the short circuit current at 2 by 20, I get 735. This is incorrect. There is no one. 735.1. And based on these two, I will choose 800 to 5. Similarly for the other ones. Okay. So this is how I choose the CT ratio based on the two satisfying the two criteria. All right, based on this criteria, it will be 200 to 5, 400 to 5, 1100 to 5. This is 150 or 200 to 5. Now we finish from selecting CT ratios. Now we choose the pickup settings. The pickup settings for the three. So as I choose now, if you go to the system again, this breaker is a feeder, a load feeder, and I will choose 1.5 here, 1.5 here. The pickup setting all, I choose 1.5. Higher than the, so 1.5, higher than your full load, which was for 131.2, divided by CT ratio of number 1, which is 300 over 5. So I'll multiply by 5 over 300, like a division. And that gives me the current referred to secondary side, referred to the relay side. And I will choose a pickup setting higher or equal to this. Now, because in the relay says, in the specification, the pickup settings in steps of 1 ampere from 1 to 12. So in the steps of 1, I would not be able to choose exactly 3.28. So they will go to the higher, next higher is 4 ampere. And similarly, we did for the other four relays. Okay. Now to determine this is, you have to be careful now when you choose the timing. This all what I did is straightforward. We have to be careful here. Okay, so for timing, I want to choose the time dial settings or TMS. So starting from relay 1, we always start from the last one, right? From the last one here is last one is number 1. So I'll choose the minimum time dial for number 1. So the fault now, fault at 1. Okay, the time dial is chosen, selected as 1. Okay. I can choose half, but half will not give me enough operating time, as I mentioned, to coordinate with anything downstreams. So to check this, suppose the fault current here, the fault current at C was, fault current at C is 4,640. Okay. If you try to find the time at 4,700, we'll see it as lower than 0.1 seconds. Now, when we don't have instantaneous relay at 1, when you coordinate between 2 and 1, we coordinate at maximum fault current at C, which is we have evaluated, we have calculated. But when we have instantaneous at 1, we coordinate this with this at the current correspond to the instantaneous value of 1. This is the main difference between coordination when you have instantaneous elements or if you don't have instantaneous elements. In these steps, the first I already select the minimum time dial, okay, for relay number 1. The instantaneous elements, I instantaneous, this is I instantaneous, I for the 50, okay. elements. Because this number 1 was a load directly, I don't have a remote bus. So we'll choose the 50% of the local fault current. 50% of the short circuit at relay 1, short circuit at relay 1 was 4,640, and I also refer it to the secondary side. I got this is the pickup setting, and because the settings in steps of 1, I cannot choose 38.6. I'll go to the next higher. This is instantaneous settings off. So I have to now see what is the current at the primary side. What is the current here, or sorry, here, at which this will operate, okay? The instantaneous relay operates. And that corresponds to, you multiply this by the CT ratio. And that gives me the current at the primary side at which this instance relay picks up. Okay, so now I have to coordinate between R1 and R2 at this value of current. So what I'll do, I want to find what's the plug setting multiplier for relay 1. Okay, and that's, you take this one times, you divide it by CT ratio, divided by the pickup settings of number 1. Pickup setting was 4, so divided by 4. So this current represents almost 10 times the pickup setting 4. And from the curve now, I'll go to almost 9.710. Okay, so we go to the curve at 10 almost. This is 10 or 9.7, and the curve was 1 time dial. So this is the point almost. So almost, yeah. Okay, almost 0.1. Okay, so the time here is 0.1 second for relay. This is for relay T of R1. Okay. At when the current is 2,340. Now I know TR1. I should add now the coordination time interval, which was in the specifications. The coordination time interval is 0.4 seconds. I added 0.4 seconds to the time that we found, which is this 0.1 plus 0.4 second. That gives me the time for relay 2. That's T of R2. Okay. Now I should know what is the settings that gives me, what is the time dial setting that gives me this operating time when the fault is 2,340. So I have to see this 2,340 for relay 2. Okay, plug setting for relay 2. This fault current, I also refer it to the secondary side of CT of relay 2, and its ratio is this CT ratio times 5/100 divided by the pickup setting of relay 2. Relay 2 pickup setting is 4 also, so divided by 4. I get, this is the current, this is the multiple, means this is almost 3.5, this fault current almost 3.5 higher than this 4. Okay, higher than the pickup setting. Now I'll go to almost 3.5 with 0.5. I'll see which curve that give me this time or higher at this multiple. So I'll go 3.5 almost, or 3.6 in the curve. Where is the curve? 3.5. This is 3. This is 3.5. Okay, well, I'm more than 3.5, 3.6 somewhere here. And the time, so this is the plug setting multiplier, and the time is 0.5. This is 0.5 seconds. So I need to go straight like this and vertical like this. Okay, and see where they cross. It's somewhere here. Okay, so if I choose 2, it will give me a time less than what, 0.5. So I'll go for this curve, which is this curve is 2, and but this curve is 1. So 1 will not give me the required 0.5 second at this multiple of current setting. So I'll choose 2 now. Based on this, I'll choose 2. So here, time dial is chosen as 2. And similarly, what is the instantaneous value for relay 2? For relay 2, I'll look at also the circuits. For relay 2, to choose the instantaneous, I have to find a fault at remote end. Fault is here. And I'll see fault here. I'll add 25% higher than this fault, and then I'll choose the settings for R2. Instantaneous settings. So it is done as like this. It's 1.25 times I fault at C. This is the remote bus for relay 2 over CT ratio of 2, relay 2. That gives me the pickup setting. The nearest value is 37. Okay, I'm done from setting R2. So this is the settings, and this is the time dial settings. Okay, the pickup setting already chosen before here. So this is the pickup settings of 2. Now I know it's R3 pickup settings. I know also I need to calculate its time dial setting. So first step before you get started, I need also now to coordinate between 2 and 3. Okay, so I should calculate the time here at a value correspond to a current correspond to the instantaneous of 2. Okay, so instantaneous of 2. Okay, this is instantaneous of 2 of relay 2. So what's the primary current at which this relay picks up? So it's 37 times the CT ratio of 2, relay 2. This is CT ratio of relay 2. And that gives me the current at the primary side that will make relay 2 instantaneous relay 2 pickup. And now I can see what is this plug setting multiplier of this as compared to the pickup settings of R2. So I'll again divide it by CT ratio and divided by the pickup settings of R2, which is 4. I get this represent this fault current represent almost 9 times the pickup setting of 2. From the curve at 9 times I got from the curve I know time dial is 2. I know at 9 point, so I go to 10 here, almost 10, and I know time dial 2, from which I get the corresponding operating time, which will be 0.18 seconds. Now I add coordination time interval to this time, which is 0.4 plus this gives me the time. This is time of R3. Okay, Now I know the time of R3, but I need also this current, which is this, represent how many multiples of R3 pickup settings. So I'll take this current again. I'll divide by CT ratio of 3 and divided by the pickup setting of 3, I get this multiple. So this current at which I calculated time of this is almost three times higher than pickup setting of R3. Now I know the multiple flux. This is the plug setting multiplier of 3, and I can now from 3.36 and 0.58. I go to 0.58, 0.5. This is 0.5. Okay, and 0.58, almost 0.6, and 3.6 something somewhere. I'll see where is the cross section between these two. Okay, and I'll find the curve that's either higher or equal to that. That gives me this. From that, I get the time dial 2 also. Okay, now to coordinate, now finish from 3, and I want to coordinate between 4 and 3. But before I get this, I need to choose as instantaneous for 3. Can we choose instantaneous for 3 with 2? In this case, it's not possible, because if I choose for instance for 3, I will choose the remote fault current, which is the same as remote current for 2, and both settings of instantaneous will be same for 2 and 3, and as a result, when a fault occurs here, this instantaneous and this instantaneous will operate at the same time, and hence I will lose selectivity that this breaker should operate when a fault is here. So in this case, when there is no current margin between two protective devices, then you cannot install instantaneous relay unless it is time delayed also. So in this case, 3 will not have, it's not recommended to have instantaneous relays. So there will be no instantaneous relay, okay, at 3. Okay. Now how do you find now the time settings for time dial setting for 4? Now I have to coordinate 4 and 3 at the instantaneous settings of 3, but because I don't have an instantaneous 3, I will coordinate 4 with 3 at a current correspond the fault at B, maximum fault at B. Same as we did in example number 1. This is the difference now. So the fault current at 3, or the fault current at bus B, the fault current at bus B is this 14,714. This one. Okay, so what is this ratio of this current to the pickup setting of R3? This is for relay 3. So I divided by CT ratio 3. This is CT ratio of 3 over pickup setting of 3. Setting of 3. Okay, it gives me how many this fault current, how many multiples of the pickup settings of 3, and then I know the pickup settings. The multiples of the pickup settings, and I know the time dial already chosen as 2 for relay 3. This is time dial 3, time dial of 3. I know time dial 3, and I know its plug setting multiplier. Okay, then I can find the time. operating time of 3. So one sinus, I will add coordination time interval to this. So that's gives me the time of relay at 4. Okay, time of 3 plus coordination time interval give me time at 4. Now I need also to change this to see how many multiples of the primary of the pickup settings of number 4. This is plug setting multiplier of 4 equal this fault current, but this fault current, the fault current here will not seen by this breaker at the same level. You have to refer this fault current to this side by using the ratio. So this is done here, where I take this fault current and using the ratio, I refer this fault current to the relay 4 side by the VT ratio, and then divided by CT ratio of number 4, this is CT4, and divided by pickup setting of 4, I settings of 4. That gives me this current represents almost 7 times higher than the pickup settings. And now I know the time, I know the multiple of the pickup settings. I can go to the curve, 7 times and 0.6, 7 times is here, and 0.6 is here. So when you go, it's almost here. Okay. This is 7, this is 0.6. So I'll go to this curve, which is 5. This one is 5. All right, so the time dial is 5. I'm finished now. The last part is the instantaneous elements for relay 4. Same thing. I will go to here. The instantaneous level here, I will finish at this slide. For instantaneous level, you should always find the remote fault current, but refer to this side divided by CT ratio by times 1.25. And this is what's done here. Is 1.25 times I fault, but this is referred to the relay 4 side. Okay, so the fault current referred to was 1689. Okay, the fault, it's not this one. When you refer this to the relay 4 side, it will becomes not this one. Current at B is this, okay, but when you refer it to the 1115 kV side, it will becomes this 1689. 1689 times 1.25 divided by CT ratio of 4. Sorry, divided by CT ratio 4 gives me the pickup settings of instantaneous relay at 4. This is for I instantaneous of 4. I'm done from the settings. So no, because this is not available, so we'll go to the next higher, which is 36. This is okay. I instantaneous 4. And all right, so we are done from the settings. We are finished up to here. We finished from all the settings. So these are the pickup settings for relay 1, which was not this was 4, and this is the time del was 1, the instantaneous element 40, the primary current correspond to this instance relay, which you multiply by a CT ratio. And there is no instantaneous in 3, right? This is summary of the settings. And this is how we draw. This is relay 1. This is the 51 of relay 1. This is the 50 instantaneous of relay 1. Okay, relay 1 at relay 1 instantaneous current was 2340. This is 2340 ampere, at which the instant relay 1 operate instantaneously. Now relay 2, this is the 51, and this is the instantaneous relay for 1. Relay 2 instantaneous relay was it was 37, which correspond to 5,920, which is this one. This is 1,000, 2,000, 3,000, 4,000, 4,000, 5,000, and 220. This is almost okay for instantaneous too, and so forth for the other relay. So this these are the 3 relay. As you can see, they are coordinated. Relay 1 works first, then 2, then 3, then 4. Okay. 3 doesn't have an instantaneous, so the curve for 50 is continuous. Okay. And these 2 curves represent the damage curve of the transformer, and this is the damage curve of the line, of the cable. And normally, the protective relays should always, the characteristic relay should be lower than the damage curve. This is thermal damage curve of the transformer. As you can see, transformer is protected by relay 4, not relay 3, because this is a radial system. So for a fault in the transformer, this will not see this fault. So 4 has to operate before the transformer get damaged. Okay, 2 has to operate before this cable get damaged. Even 3, okay, it will protect the cable as a backup with this. So when you go to 4 with damage curve of 4 of this 4 and damage curve of the transformer, it's below the damage curve of the transformer. If the 4 becomes like this characteristics, then it means at this current, the transformer get damaged at this time, and the operating time is this, so it won't be suitable in this case. So always the protected devices has to be below the damage curve of the protected device. And similarly, if you look to line 1 characteristic, which is this, and line 1 is protected by the line characteristic. This line is protected by 2 and as a backup by 3. So both 3 and 2 has to be below the damage curve of this cable. So as you can see, number 3 and 2 are below the damage curve, except here at this current and beyond. At current higher than this value, okay, you have, but you might see that at 3 you will not see any current higher than probably this. You can see R3 won't see a current higher than R3 will not see a current higher than fault current at bus B. Okay, at bus B fault current is 1,000, 14,000, 13 kilo ampere, 14, almost 15 kilo ampere. This is 10, and this is 10 kiloampere, okay, 20 kiloampere, so 15 somewhere here, so there's no issues of this. All right, so I want you to read the remaining here. How do we set the, how do you know the instantaneous relay, which is here, the 50 relay, what is the percentage of the cable length that will be protected by 50, the instantaneous relay offline at breaker, at breaker 2. Okay. This is at breaker 2. All right, so with this I will close this chapter. I want you to start also the assignment on this, and next week I'll give you a quiz on this chapter. Okay, مع السلامة. I will stop the recording now.